One, of course, that's a play. Oh no, it's a PDF. It can't animate. I really like this animation. It's the nicest thing I've ever made. But this was shown at SC last year, so working with our friends at UK AEA on some physics-informed neural networks. Again, something that is kind of a relatively new field, and somewhere that surprisingly small models actually can give you a really interesting benefit in their ability to learn how to solve PDEs. So PDEs that in this case it wasn't hard to solve, it's a wave equation, but things that are the idea of the application is things that are hard to solve analytically, or maybe not possible at all, hard to solve numerically. All of the maths to do the differentiation and whatnot is built into the machine learning frameworks anyway. So why not repurpose it the other way? We have a loss function that might learn the PDE itself, have a loss function that relates to the boundary conditions or the initial conditions, maybe some data-driven element as well in the case where we're not convinced the PDE is that well posed across the whole domain. Things like this we can combine all together and just effectively let it loose. And it might be that model isn't complex or the right design to be able to learn more complex features of a particular solution, but typically by letting it loose, you're letting the whole system relax in effect to try and minimize all these losses. So your boundary condition should be 0, so you just have one loss function that is just f of sort of x, y, z at the boundaries. And if that's miles away from 0, then that will contribute towards the loss. So the model will then keep learning and try to minimize that. So really interesting cases there. Because I'm not going to try and go full sales mode here, but I can't not talk about the performance when normalized for the cost of the system end up being about 11x faster than A100 GPUs. Part of the benefit here being that the whole model sits in the SRAM of a single chip, and so just flies. We used 2 IPUs data parallel just because cost-wise it kept it more similar, and we got pretty much 100% scaling speed up there because it's quite a nice nice model. That's quite fun. On to more kind of broad hot topics in research, and this is kind of looking to a bit more cutting edge on the ML side rather than the what are you using it for side. So some of this is a bit more kind of where are the models going, rather than in some cases the neural network architecture might be not a huge brand new kind of model, but you're using it for something that's never been done before. That was at the previous slides. Now we're looking at more at where things are going. So graph neural networks do seem to be getting a lot of traction, a lot of popularity with these. The general idea is, and I mean, a lot of situations in the real world can be represented quite well as graphs. The idea you've got some graphs of maybe people in a social network, and they have certain connections depending on whether they're friends with each other or whether they like the same thing. Maybe they've liked the same page on Facebook or whatever it might be. And then you can try and use some properties of this to either predict a potential link, should these two people be friends, or predict some kind of properties about the person. Do we think they will be the sort of person who could be targeted by this mass evil advertising campaign or whatever it might be? There's a lot that you could do with that. That's only one example. Obviously, it's probably a more evil one, but the idea is you can have this these kind of GNNs that can pass messages around. You're passing that through a small neural network within that, and then rinse and repeat to learn different sort of feature embeddings. They're called this sort of features that don't necessarily make sense to a human, but they can be used to predict things within the network. So I say there's tons and tons of applications. People talk about GNNs as if they're an application, and they're really not. It's like talking about convolutional neural networks, so you can use them for whatever you want, really. It's a hugely broad, it's broader than that, really. A graph neural network is just any old neural network that runs on a graph. So it could be any kind of architecture you want, any types of layers in there. It's very, very broad. The idea is different than just passing in an image or something sort of with a more regular structure. But yeah, there's lots of different approaches here, particularly things like drug discovery. So you've got some protein structure that you can represent as a graph. And so the node properties are what are the atoms, the edges might be what are the bonds between atoms, and it all kind of, you can imagine it's quite a nice analogy. It makes sort of sense. You could use GNNs then to predict potentially the function of a new drug that you're trying to synthesize, particularly if you're trying to make new drugs to treat rare diseases. Typically it takes a very long time, but also of thousands and thousands of candidates that you come up with, very few, if any, will make it anywhere near clinical trials. So if you whittle that down much more quickly to here's 100 good-looking candidates rather than 11,000, they might be okay, they might be all rubbish kind of candidates. That could be very, very good, not just for saving rich pharma companies money, but more getting the drugs there in the first place, because we could start looking for things and trying new ideas in a much more clever way. One example I'd like to point out, we talked about yesterday, SNET. We've been working quite closely with PNNL on SNET. At the time, I think it took quite a bit of effort to get things ported over to the IPU because we didn't have support for PyTorch geometric. Fortunately, now we do, which is lovely. So these sort of things of these kind of working with different labs has fed back into our software stack, helps us work out what do we need to focus on, what support for what frameworks and various features is really important to users. And so this is one example that sort of fed back into there. And it was noted yesterday that sort of to contextualize the time needed to train some of these models on 4 big NVIDIA GPUs, it took about 65 hours. On the IPUs, again, same money's worth of kit, took 98 minutes. So that's the kind of things that we can see for the right kind of model, right kind of situation that can really help. As an interesting point, there's a lot of things about graph neural networks that support the kind of architecture that's on the IPU. So you've got lots of different cores, as we say, and the memory on that. If you're passing messages around on the chip rather than bouncing back to HBM, back and forth, that gives you a much higher bandwidth, so your communication patterns are a lot better. We can scale that again to more chips as well, communicate between directly, but typically that kind of memory bandwidth limited scenario that you often see in these kind of GNN applications does suit certain architectures like the IPU better than the GPU. Of course, if you get to something that's just enormous images, for example, then that might be a slightly different way around, or there might be some models that are equally good on both, but particularly GNNs, we see some huge speed ups, like 60 hours down to 98 minutes. That's pretty cool as well. A quick note on some more foundational models. So we'll talk a little bit about ChatGPT, things like that, and then I probably will have to shut up at some point and let people go to have some food. So of course, we're all familiar with ChatGPT by now. I'm sure everyone's at least heard of it, if not had a go themselves. I did manage to get it to generate a nice sitcom script about Graphcore before Christmas. That was quite fun, but undoubtedly very, very powerful. The trends we were hoping at one point, particularly when we were designing with the previous version of the IPU chip, because we can look at a lot of more fine-grained features in a model, or sparsity, or things that are hard to vectorize very well with the IPU. The hope has always been that people will start to try these kind of tricks, get more efficient with their models, work cleverer rather than harder, rather than models just getting bigger and bigger. The truth is kind of both happened, really. Models have got bigger and more intricate. So, so as things go along, there's a lot of new challenges, but certainly things like ChatGPT based on GPT-3, future versions of GPT-4 and so on are only getting bigger. The kind of capability of these models is enormous. The idea that you can talk to it at that level, you can have it almost write a section of your thesis for you, and it doesn't lose any conviction whether it's right or wrong. It's like talking to a drunk Oxbridge PPE student in the pub, but it can write things really convincingly and really well. If you want to formalize it, I know what I want to say in this email, but I don't know how to write it. It's really good at things like that. Thing is, though, of course, what happens when all you want to do is do some natural language understanding, not generation, just understanding. You want to say, analyze the sentiment of these 5 million research papers, or these sentences, or whatever it might be, that you just want to get the general sentiment, or does it agree with this statement or not? GPT-3 and 4, ChatGPT, massively overkill for that sort of thing. That's where we start to get to the point where it's impressive, it's getting a lot of attention. People on YouTube who normally just show you brand new iPhones and things are talking about ChatGPT, but it doesn't mean we should use it for everything. So we've got these enormous models with enormous capability, the multimodal ones where they can do images and text, things like that. But the cost is getting higher and higher. And if you were to run ChatGPT paid for in sort of a deployment where you were doing very simple tasks, you could be paying hundreds of times more than you really need to, because it is just massively overkill. But there isn't like a ChatGPT Lite. You can't just say, only give me this capability, because it doesn't really exist within that. So how do we get more efficient? This is another thing we're particularly interested in. One example is being sort of more selective with the way we put models together. There's a lot of research going into things like mixture of experts. So you've got a model constructed of different parts that specialize in different types of tasks. So the idea is a bit like human brain. CT scans, depending on what tasks people are thinking about, light up quite differently. There was a chap in the US in the late 1800s working on the railroads who, in a rather Tom and Jerry fashion, managed to somehow pickaxe himself in the head. And amazingly survived. There's a lot of brain damage, but his general kind of ability to think and reason were relatively unaffected. His sight was fine, everything was fine, but his personality had massively changed. Apparently afterwards, he really wasn't a nice guy, but before he was lovely. So things like that, the idea that different parts of the brain are doing different things in a similar kind of fashion. We could train a huge model on lots of different tasks, lots of different media, text, audio, images, videos, and so on. It could learn much better about the interplay between all these than any individual part of it just trained on one type of data ever could. But we don't need to run the whole thing for every task afterwards. If we could selectively prune off parts of a model and then use that bit that's now become really good at human language understanding in text form, that could be more powerful, but also efficient at the same time, things like that. The other thing to note, as I sort of touched on briefly, is sparsification. So if you've got a big sparse matrix you want to do some operations on, if you naively vectorize that on a GPU or something like that, you're going to get a lot of wasted cycles doing sort of x plus 0 equals 0, effectively. So x rather. There's no point doing that. If you can cut all those out, if you can just keep the non-zero parts of the tensors that you care about, then we can be a lot more efficient. But of course, that means doing lots of irregular sized operations that effectively are different operations at the same time. So again, different type of architectures like the IPU can suit that very well. And you can reduce your model size down, because if half your model is just full of zeros, what's the point having that half? If you can efficiently keep track of where the non-zero elements should go, then you can make things a lot more efficient as well. And I've already said what that is, but in effect, we're just sort of severing parameters that we don't need to be more efficient. It's just not trivially parallelizable if you assume that parallel means vectorized. Final thing to note, this is the last thing, I promise. The good computer. Now, I talked about the existing IPUs. This is a bit of a nod towards the future. The existing IPUs, I would say, are very good. This isn't to mean that good isn't to say that our previous computers aren't good. Good is named after a researcher called Jack Good, who in the 60s proposed the idea that we need some kind of a computer that's more intelligent or more capable than the human brain to tell us how to survive. Otherwise, humanity will perish, which is quite morbid. But the idea is, let's see, can we build a computer that by some metric, it might be quite hand wavy, it might not be rigorous, by some metric is more capable than the human brain. So the idea is the roadmap to auto intelligence, we're going to see if we can build a computer more powerful than ourselves. So the human brain has 100 billion neurons, 100 trillion or more synapses. If we take the first step of hand waviness and equate synapses to being like parameters in an AI model, then we can think of it as, okay, we need to build some machine that can cope with models that are 100 trillion or more parameters. The largest AI models around are about 1 trillion. That's about as big as we've got so far. We're developing machines of the future that can scale to bigger than that. So we're talking about earlier the scaling efficiency of going beyond DGX boxes, for example, and that dropping off rather dramatically. Yeah, scaling that up to 100 trillion isn't going to work. We need something different approach. Similarly, we're sort of big enough and wise enough now to admit that scaling lots of chips with just SRAM, you need a lot of chips for that as well. So at the moment, with the current IPU hardware, we can do a lot of models really well, but we can't do that. So we also need some machines of the future, and that's where the good computer named after Jack Good comes in. So the idea is very, very scalable. This is our, this isn't a military formation, this is a big data center. The idea is we've got lots and lots of IPU machines in there, very much linked together, highly scalable, sort of high bandwidth between them. Similar kind of chip architecture to what we do now. So 3D waveform wafer logic stacks, power delivery, and then logic wafers on top to give us that SRAM, that highly parallel, no need to vectorize, you can be a lot more flexible kind of approach, but also with access to lots and lots of memory off the chip with high bandwidth. So the idea is similar kind of bandwidth per chip to the leading GPUs at the moment, but memory sort of 5, almost 10x more per chip. So rather than 80 gig, we're talking half a terabyte per chip. So much, much larger, because a lot of these big language models, particularly for training, actually a lot of the model, the bits that you're working on right now, you want that bandwidth to keep your computations nice and quick. So the on-chip memory, the SRAM, is very, very useful. But other parts of the model that you're not going to touch for a little while, you don't need to have everything right there all the time either. So we reckon for an enormous 100 trillion parameter model, we want to be able to do a wait update every second as a ballpark, which is where these demands sort of come in. The idea is we'll be able to go to about 500 trillion parameters with this, and I can't tell you how we know how to do it, but we know how to do it. So we don't know how to build a model. We're hoping someone else can do that, but we know how to build the machines. So this will form our machine in the future. Again, we're hoping that someone will be able to build it as well, in terms of buy all the kit and put it together, because we're certainly not going to build one ourselves and just leave it in a room somewhere. We're also going to work with huge external partners. Maybe Rishi Sunak can put the bill with his 900 million promises. But this is what we think will be the future: IP technology with the extra off-chip memory and bandwidth, and allow us to go towards this exascale promise. I don't think I need to say any of this really. We know what in this room what sort of application we're looking at here. The sky's the limit really. Things that we just can't do at the moment is the idea. As I was saying yesterday, a lot of the applications in surrogate models and things, the models are quite simple at the moment because people are starting off, but very quickly the demands are going to get bigger and bigger, and we think that this is going to be the hardware that one will need to go to the real sort of the full scale. When we get digital twins of things that are really, really complex, suddenly single chips aren't going to cut it in that sense. So that's where we think it's going. One thing to note, some of you out there might like to have a go with the current hardware. So we've partnered up with a company called Paperspace, who do IPUs in the cloud and GPUs and everything else, but obviously IPUs are the best. And you can access these chips via Jupyter notebooks. So lots of examples on there that we've put on there, lots of example applications. Stable diffusion you can run in the cloud for, give it an image and then say redraw it in the style of Matt Groening, who draws The Simpsons, things like that. Lots of other applications we've got on there. We have a GPT-J, which is an open source GPT model for language understanding. And a lot of these models you can run for free. So you can have a 6-hour trial running either our examples or whatever model you want. If you've got your own Jupyter notebooks on IPUs in the cloud, after 6 hours, it will stop. And then you just press start again and you get another free 6 hours. If you want a bigger machine, more storage and so on, then you can consider giving us money. But to get people just to be able to try the hardware, no commitments, you don't need to worry about, can we put it in the lab, anything like that. Just have a go and see how you get on. And feel free to ask us some questions if you do run into any problems. But QR code there, or if you just search Graphcore Paperspace, it'll come up. Do feel free to have a look there. And I'd be more than happy to work with any of you as well on any projects. So
thank you, Alex. Thanks very much.